Today's the topic du jour is not small modular, meaning nuclear reactors. It's the difficulties of SMRs. Because we heard a previous talk on the sizzle, how are they going to save the earth and all the stuff, and how it's just zoom and everybody's going to invest in it because it's so wonderful. So I thought I would explore it a little more scientifically. What I did was I asked Claude and I asked Gemini and maybe one other to give me slide decks for this talk, thinking, let them do the talk. And they gave me some slide decks. And they weren't quite right. But I did use some of their slides. And whenever I use any of their slides, I put the company logo on there so you can know I use the slides. And I didn't want to alter the slides at all. But this first one was too boring. So I got this GIMP video right here. I'm obviously I got it. It's a GIF file for here. And it shows a neutron hitting a nucleus and splitting it in half. When I got it from, I downloaded from the internet from somewhere, it was at 200 frames per second. It went too fast, you couldn't see it. So then I put the video into GIMP, slowed it to 30 frames per second, and then put it into that slide to give it, so I can give the slides a little more activity and some motion. So Claude did not provide the GIMP file. I get full credit for that. Now, what Claude wanted me to do was talk about nuclear. This is pretty good. Nuclear fission, light water reactors. Light water just means ordinary water. It's not tritium, it's not deuterium, it's just ordinary water. Talk about small modular reactors and the technical challenges. I changed it a little bit and how it goes, but well, kind of a lot. So what we're going to start out with is another Claude slide. This is a nice one. Nuclear fission and how it really starts. And the key concept is that the amount of energy in mass is, the total amount of energy is matter times the speed of light squared. And if you can do a little arithmetic, you know that if you multiply anything by the speed of light squared, it's going to be a big number. There's a huge amount of energy in it. And nuclear fission only uses 0.1%. It's actually 0.09, well, 0.1% of the energy available in matter. But you multiply that 0.1% by the square root of light, the square of light, speed of light squared, and you got a big number. So if we look at U-235, that's the main element we'll be talking about. It gives off, well, each split gives off 200 million electron volts. So if 1 kilogram of U-235 gives 80 terajoules, means trillion, 80 terajoules of energy. Natural gas combustion gives 55 megajoules. So the ratio is 1.4 million to 1. So you get a huge amount of energy, 1.4 million times as much energy from a kilogram of U-235 than you do from natural gas. That's reported in proportion. Now, what we're going to do first is go back to our good friend, the periodic table. And what we're going to look at is this group called the actinides. And it's a special group. It doesn't fit on the periodic table. That little box is this whole green line down here for the group that's in the actinides. And the important actinides are uranium today, plutonium, and californium. Now, there's very little californium in the natural environment. Californium has a half-life of 2.5 years. So anything that came in the early formation of the Earth is long gone. It arises from the degradation. We're going to talk about beta decay from the lower actinides. And we'll go over that because that's a very important part of nuclear chemistry. It's called beta minus decay. And people refer to it as beta decay, called beta minus because it gives off an electron. And the way beta minus decay works is, and this was looked at by Wolfgang Pauli in the 1930s, a neutron will break down into a proton, an electron, and give off a gamma ray. And we're going to keep coming back to this over and over. It's fundamental to nuclear reactors. But what Pauli found was that his measurements were off by 1/1,000,000th. When he totaled up the proton energy, the electron energy, and the X-ray, it was off by 1/1,000,000th. And he repeated it, it was off. And other people did it. It was off by 1/1,000,000th. He came up short. And so after some discussion in the 1930s, and this is 1930s now, they decided that they believed in the conservation of mass and energy. Therefore, there's something else there. And they didn't know what it was because they couldn't find it. But it was very small, and Pauli and two other Italian scientists of Italian extraction named this particle they couldn't find. The diminutive in Italian of neutron, which is neutrino. That's how it got its name. But it wasn't until the 1950s that there was a hint that it existed. It wasn't until the 1990s that the neutrino was shown to exist. It took a long time to actually find it. And when you get beta decay, we'll call it beta decay. We start with uranium. Uranium undergoes beta decay. It gets one more proton, and you remember from the periodic table, when you go up by one proton, you get a new element. And you go up another, say the neptunium, go up another beta decay, you're going to get plutonium. And you keep on going up, going up, going up, and then you finally get to californium with each beta decay. These will all have the same atomic weights because they've traded a neutron for a proton. I should say, without getting ahead of myself, is these elements have lots of isotopes. They're lousy with isotopes. So, but in this particular example, we did 240 to 240 to 240. What's interesting is curium has no stable isotopes, nor does californium. So now we get to our friend Enrico Fermi, the last man to know everything. And he looked at this energy equation, and he wrote in 1923, "It does not seem possible, at least in the near future, to find a way to release these dreadful amounts of energy, which is all to the good, because the first effect of an explosion of such a dreadful amount of energy would be to smash into smithereens the physicists who had the misfortune to find a way to do it." So he understood how vast this power was. Now, he had an accidental discovery in his laboratory in Italy. He was bombarding silver with neutrons to see how radioactive it would become. And what he found was when the neutron source was placed on a wooden table, it caused the silver to become more radioactive than if you put the neutron source on a marble table. Now, only in Italy would you have a marble table in a laboratory, but he had one. And he thought that was incredibly mysterious. And he went outside the very same day he found this phenomenon to a pool on the grounds. And he put the silver underwater and bombarded it with neutrons. And again, it became more radioactive than it was up in the air. And ultimately, he came to the conclusion that carbon and water slowed down fast neutrons, enabled them to stay there near the nucleus longer. And when it stayed near the next nucleus longer, it's more likely to cause a collision with it. And each neutron collision with carbon reduces neutron energy by 28%. So carbon, or the term is it moderates it, means it slows it. And for this minor discovery, he was given the Nobel Prize in 1938. Now, as you all remember, it's given in Sweden. But in 1938, in November of 1938, the Italians, it's given out in December. In November of 1938, the fascist regime Mussolini passed the leggi razziali, which are the racial laws. And the racial laws stripped Jews of their assets and prevented them from immigrating. And Fermi's wife was Jewish. But they did give him and his family, his wife and kids, permission to go to Sweden to get the Nobel Prize, which he did do. And then after he received the Nobel Prize, he got on a ship and sailed to America and never returned. Nice move, Italy.
Extended sabbatical.
That's extended sabbatical. Well, and so.
What the wrong thing.
Right. So here's what we're going to be talking about all day. Neutron hits a target nucleus, and it breaks into two fission products, two and only two. And these can vary. These are new nuclei of various combinations of protons and neutrons. It's not the strict splitting in half. It also gives up to free neutrons to fly out. So Pauli goes to Chicago, and under I guess it was a squash court, they built the Chicago Pile 1. And they assembled uranium metal 6 tons, uranium oxide 40 tons, and they fitted into holes drilled into graphite blocks. Graphite's carbon. That's the moderator. It's going to slow down the neutrons. And they assembled it 15 days in 1942. So now here's what Claude wants me to tell you about what they call the chain reaction neutron economy. If the split, if the new subnuclei and the neutrons go out, if the neutrons hit less than one other atom, less than one other atom, you'll have a subcritical reaction that will die out. If it hits approximately one each, it'll be a sustaining smooth reaction. And if it hits more than one each, it has a supercritical reaction that exponentially grows like crazy. And so it has to be controlled.
How can K less than 1 be something other than 0?
Well, 0.8 on average.
Okay.
It's on average less than 1.
Yeah, it's not a single one, it's a bunch of them together.
Okay, all right.
So now we're going to look at, and we'll talk about what this neutron source will be. But here you got a neutron, it hits U-235. Briefly, it goes up to U-236. And then it splits. I use this example of krypton and barium, but there's all sorts of double splits. And 2 to 3 neutrons, it actually averages 2.4, plus 200 million electron volts for each collision. So that's a lot of energy. So the average of 2.43 neutrons emitted per U-235 fission. And one must cause the next fission for criticality. Prompt means fast. Prompt neutrons have 200 million electron volts, but they have to be slowed down to thermal energies of 0.025 electron volts for efficient use of light water reactors. So you got to slow them down a lot. So we have two terms to remember: delayed neutrons or slow neutrons, which is only 0.65% of the total neutrons released, are critical for factor controllability, and they extend, and we talked about the effective neutron lifetime. So here are the breakdown products of U-235. Now you can do a distribution of the mass numbers. Here's the mass number, and here's how many of each element there are. Show it there, and if you start looking at the list, there's a lot of them. Things are like crazy when these reactions occur. So there's a lot of them. And you have the lighter elements over here, and then the heavy elements here that you'll find. A whole list of them, from bromine, krypton, zirconium, a lot of stuff, lanthanum. But in this, we look at xenon. Xenon 135. Now this is real hyperbole. They call it the reactor killer. Well, what xenon 135 does, it absorbs neutrons. So if it absorbs neutrons, less are available to hit on the U-235. So it slows the reactor. And ultimately, if it builds up too much, it'll turn it all the way off, which is no big deal. It's done all the time. It's no big deal. They give it a name, reactor killer. And to show you the reaction, here we start with xenon 135, and it can beta decay to cesium, which is stable, or you can pick up a neutron inside a reactor, go to xenon 136, which is stable, and that happens very fast. So xenon 135 poison is not a major problem, but it can become one. Here's Chernobyl. You'll remember Chernobyl. Buy a condo there, sounds pretty good. But you'll see after, xenon poison became a problem. Now notice this building here and this building there, hardly affected. I'm sure it's affected some. Oh, this is the only little explosion. It was more like a rapid campfire. It wasn't a nuclear explosion. It wasn't that. It's just that, as you all know, they released huge amount of radiation into the environment. That was the problem. It wasn't the destructive power of the popping of the reactor. So what happened at Chernobyl? Well, George Santayana said, those who cannot remember the past are condemned to repeat it. That's why we want to go through this as we talk about SMRs. What they had in Russia was the RBMK, which is, here the Russian word is reactor large power channel type. RBMK had fuel in pressure tubes surrounded by the moderator, graphite. Western power, we use mostly water vessels. We don't use these very often, graphite. So here's the Chernobyl graphite moderator system. This is just a drawing of it. The orange here is the uranium. The black here are the boron rods that will absorb neutrons to slow the reaction. And then you have so the moderator is graphite and the coolant is water. So water is pumped in here, it gets real hot, goes to the steam separator. Here it goes down the steam separator. Goes down the steam separator here, steam drives a turbine. And the other water precipitates out, maybe add a little bit more. And it goes around, around, around and drives the turbine. And if it's going too fast, you put the rods down. If it's going too slow, you pull the rods up. So the key point here is the water is the coolant and graphite is the moderator. And to get a little ahead of ourselves, east versus west, our moderators are water and RBMK used graphite. Our coolant is water. They had water in tubes going by the graphite tubes. We have a pressure vessel. We use a single large pressure vessel. They used individual channels. Around our power sources, we have a full containment vessel. Chernobyl had none. It was just a building. And so our reactors have what's called a negative void coefficient. That means if something bad happens, the reaction slows to a halt. For example, if the water boils off, you've lost your moderator and it'll slow to a halt. So it's a safety feature. They had a positive void coefficient, but when they lost the water, if they lose water, it just gets hotter and hotter because you get the graphite in. So it's a positive void coefficient. And ours are small and theirs are very big.
Compare that to 3 Mile Island.
We're going to do that. Now, the Russian reactors surround their tubes with graphite. If the reaction got out of control, boron graphite rods had to be inserted from above. There's lots of elements. You can use cadmium, indium, you can use a lot of stuff. They use boron. And they have this called the SCRAM maneuver, Safety Control Rod Axe Man. And this was with Fermi. And Norman Hilberry, he was a physicist at Pile 1, and he truly stood with an axe above their controller rods. And they had tied with a rope. And if anything got out of control, they were going to rely on pulleys and motors. And, rats are going to axe that rope and poof, down like that. That's called a scram. He never actually did it. But that's what a scram is. So now the xenon story. Let's get a little scientific, because this is what happens when you don't know stuff. Now here I give an example of U-235, and one of the halves is technetium. I didn't put in the other half. Now technetium will go to iodine. Now, this should be 235. I'm sorry, I made a mistake. These are all, no, it's 135s. It's half, right. It's 135, it's going to undergo beta decay. So its total atomic weight is the same. It has one more proton, so it's now changed elements. Goes from technetium up 1 to iodine. And then another beta decay, and it goes to 54 protons, and so iodine becomes a xenon. And xenon undergoes a beta decay and it becomes stable cesium. And if we looked at the time course, technetium takes 11 seconds to become iodine. Iodine takes, this half-life I'm talking about. Iodine half-life to xenon is 6.6 hours, and the xenon half-life to cesium is 9.2 hours. But here's the secret in the reactor. If you have a neutron kicking around, they're flying around like crazy. If the neutron hits the xenon, it'll decay in minutes to xenon 136, which is a stable noble gas. So if you have your reactor punching along, neutrons flying around, xenon won't build up because it'll get hit by neutrons right away and be gone. Okay, so you don't have the xenon poison. So now the Russians wanted to do something which was inherently reasonable. Here are their controller arms, control rods. Here they're down, here they're up. Here's the hot, see how it's hot? Here it's cold. So what they wanted to do was they said, if there's a loss of internal power, we have backup diesel motors that could power the boron graphite rods down to the grid in 75 seconds. They wanted to know if powering down the residual turbine energy could be used to push the rods down, because the turbines are heavy and spin, and push the rods down faster than 75 seconds. That was a very reasonable thing to do. Just power the thing down and see if the rods could be powered down. You can always use the diesels. Now, this is where you get into the cultural part. The reactor was powered down, but the regional electricity dispatcher called the plant and told them that low power was needed for a few more hours. So iodine began to build up in the system because they didn't have all those neutrons flying around. So what you have is uranium, is yttrium, and now here the two split products, yttrium and iodine. And the iodine takes 6.6 hours to become xenon and 9.2 hours. So it starts to build up because you don't have that extra neutron that's going to bump this up to xenon 136. So the xenon poison begins to build up. Not a problem. Your reactor will just grind to a halt. Not a problem. So the test was delayed for 9 hours, and the xenon 135 pit was growing. Not a problem, just slows the reactor down. But then the xenon trap springs. It was powered down from 16 to 1/2 power, which means 1,600 megawatts to 700 megawatts. Iodine continued to convert to xenon 135, which absorbs the neutrons, and then the power fell to 6 megawatts. No big deal. The technicians wanted to close the reactor, let the xenon decay. You close it for a day or two, the half-life, it just disappears. Decay to cesium, but the manager who wanted to call comrades wanted to call his superiors to tell him that he had done the test as ordered and to tell him the results. So he insisted that the test continue to see if the power rod insertion would work from the turbines. He insisted they go on and not turn the reactor off. He demanded that the power be restored rapidly by removing almost all of the graphite boron rods. They reduced the rods to 6. Regulations required a minimum of 15 rods in place. So they had the trifecta. When the test continued, coolant pumps coasted to a stop. Coolants coasted to a stop. Core temperature rises fast. The uranium heated, water no longer circulated to become steam, wasn't moving any heat from the core. Neutron rods were available. Neutrons became more available because the boron rods were out because they pulled them all out. More neutrons reached the graphite. So what do you do now? Lower the boron rods, right? And you'll be all set. But alas, the boron pellet-filled graphite rams were built with pure graphite tips, so the insertion initially created more slow neutrons, which split more U-235. Time from the graphite tip entry to explosion was 4 to 6 seconds. Whoops. A big whoops. They didn't understand what they had. So this is called human error. Okay, plus the cultural thing of wanting to get the test done. Now, you can buy a replica graphite, Chernobyl graphite rod on eBay. So now let's talk about light water reactors. 80% of our global fleet is light water reactors. A light water reactor, which is ordinary water. You have a core here, and this is all water in here. And here's your uranium and the little black things and the other control rods. And water comes in at the bottom, heats up, comes up here. Probably should have put the graphic that I got, it really should be up here. But the water comes in and heats the secondary chamber, which is water, creates steam. Steam runs to spin a turbine, goes to a generator, and then the water goes back into this bath here and circles around and around. And you can use silver, indium, cadmium, we use boron carbonate for your rods. That's a pressurized water reactor. And here's the full containment vessel that we have. There's a full containment vessel here. So what you have is a core architecture. You have your fuel assemblies, uranium oxide, ceramic pellets. You have your control rods. You have your moderator coolant, water, slows the electrons and slows the neutrons and cools the water. And you have your your pressure vessel, which contains the entire core. That's quad. So now let's look at 3 Mile Island. There's a Ken Burns effect here. These are the water towers here. I'm not quite sure where the reactors are in all this. These are the water towers in the Susquehanna River. So what happened here? Here's the reactor. Now, the principle is that for an accident to happen, multiple factors have to go wrong. What they had at TMI was a stuck open pressure relief valve for the steam. See the steam coming out of this one. And they had misleading instrumentation about the pressure relief valve. The indicator light meant that closure signal was sent, not the valve position. So you press the button to close the valve, you get a green light. You'd think intuitively that the valve is closed, but it's also only said that the signal was sent. The valve position light was out of sight of the operators, which had to be a huge design error if they didn't know whether the signal had been received. So it was stuck open, and the pressure dropped and water started to boil, especially at the core. But very quickly, steam accumulated in the core and pushed the whole water level up. Didn't have time to rise through the piping system. So the whole water level rose. And the water at the top was rated as full because it's being pushed up, even though it was actually losing water. And the operators turned off the emergency water refill because it was full. It would overfill. So now remember, water was the moderator, has negative void coefficient. Water is the moderator. The reactor went to 7% power. It was enough to overheat the system without water cooling. And that's all that happened. It did not breach the walls. It did not spread anything, but it created tremendous news. So here's TMI in the middle of the Susquehanna River. The temperature of the core number 2 rose to 4,800 degrees. Core 2 melted. It did not breach the steel walls. So they sat on it a few days, and they ended up with xenon-133. I'm not sure why. And they released xenon-133 and krypton-85. These are inert gases, noble gases. They're virtually insoluble. So even if you breathe them in, you don't absorb them. And it was intentionally released to reduce the pressure. And they released somewhere between 2.5 and 13 million curies of inert gas, which is not very much. And there was no significant environmental contamination, but there was a lot of hoopla about it, that's for sure. So on these devices, what you have on these nuclear reactors, you have your primary loop that we showed you with the radioactive material and the coolant and the moderators. You have a steam generator here, and then you may have other loops, secondary and tertiary, to get you away from the radioactive source. But ultimately, you're going to put it into a turbine generator. Now, safety systems, active versus passive. Here we get the SMR business. The conventional light water reactor requires AC power and diesel backup generators. Emergency cooling system relies on pumps. It demands operator action and monitoring 24 hours a day, 7 days a week. Vulnerable to station blackouts. And we have lessons from TMI and Chernobyl, not so much from Fukushima. With the SMRs, no electrical power is needed for its safety. It uses natural circulation, not pump-driven flow, to remove heat. Gravity-fed reservoirs rather than pump, electrically driven. Passive containment using cooling air convection. And the target is for them to shut down safely for 72 hours, or give people time to get in and take care of them if there's a problem. Now, looking at the economics, the typical reactor produces 1,000 to 1,700 megawatts, has 32% efficiency, fuel change 18 to 24 months, and costs me a paltry $6 to $17 billion. So this has a large capital cost, 10 to 17-year construction times, leading, of course, to cost overruns and financing difficulties. Requires site-by-site custom engineering. You can build the same reactor 5 times on the same area, but your different areas will require different reactor configurations. So each plant is becoming less and less now, is essentially a prototype, although less now. But these failures define the SMR value proposition, which is it's made in the factory. So it has what's called horizontal efficiency. Vertical efficiency is when you build 5 reactor towers the same. Horizontal efficiency is like Henry Ford. You got to get a line, a production line. You just make one after another, like Fords. Shorter schedules for production and modular scalability. So let's look at some of the SMRs here. You have a primary system of core steam generators, things like that. Passive safety systems, factory fabrication, modularity, and flexible siting and loading. You just put them on a truck and bring them to wherever you got to bring them. So let's look at the first SMR that we all remember was the Nautilus. And that was truly launched January 21st, 1951. And the chief engineer on the project was, much to my mother's joy, Hyman Rickover. Hyman Rickover, his name is Chaim Gadala Rickover. For those of you who can read Hebrew, it's Chaim Gadala Rickover. He was Jewish. The Navy didn't have a Jewish admiral and wasn't particularly interested in having one. But he was so popular at the time in the popular press, they had to make him an admiral, much to my mother's joy. So now let's look at the design landscape, what's going on here now. We have some light water reactors, new scale, that uses water as coolant, the moderator. We have molten salt. Molten salt uses something called, like this flybeam, which is fluorine, lithium, beryllium. So there's another one we'll use high gas temperatures, use xenon, Xe energy xenon 100. They use helium as the coolant and graphite as the moderator. That's going to be interesting. Then there's using liquid metal like TerraPower and natrium. I think Bill Gates has used this in TerraPower. And then we have the microreactors, which we're not going to talk about, 1 to 10 megawatts for remote off-grid siting with minimal staffing. Now, who would want that? I think maybe a logging camp or something like that. Well, guess who's funding it? The United States military. And I wonder why they're funding microreactors. They fit in the back of a truck and you have a base with power. Anywhere you want, you don't have to have generators and all sorts of stuff. So that's why they're funding that. You know, anytime there's something, the military figures out how to use it to kill people. They're very good at it. So I'm sure you now all speak Spanish.
What's the problem?
Right. Fuel, heat, metallurgy, waste, and the workforce. So what they're using is HALEU, which is high assay, 20%, low enriched uranium. And what HALEU is, it's 20% U-235. And most SMRs use molten salt like flybeam. HALEU uranium is converted to uranium fluoride, which is the energy source. And for reactor size reasons, you need a lot of U-235. You need it enriched to 20%. Now, this is not a problem. It wasn't a problem, except where it is a problem. That Russia was the main supplier and very responsible. So if you're a country and you want enriched uranium, you could buy it at a much cheaper price than you could make it. And since you didn't have centrifuges and all this stuff, you couldn't concentrate it further for nuclear bomb. You had no capacity to do that. And there was no financial reason to buy, to make your own uranium, to enrich it and to enrich it to 60 and 90%, unless you happen to want a bomb. We can't imagine who would think of that. So there were and are plenty of security concerns, which is now, of course, frontline news. Now, when you have any reactor, but when you have a small reactor, you want to get as much energy out of that as you can. So you want a very high temperature gradient. Here's where the problem comes in. You want it very high on this side of the turbine and very low on the other. So you use all the heat for energy to spin the turbines. You want that. Let's use water, for example. You want it real hot. And if you want the formula for that is, here's the cold temperature, here's the hot temperature. So the bit larger this gradient, the smaller this fraction, so that the temperature that's transferred would approach 1. So we want to transfer a liquid to be as hot as possible. But water is a problem. If it gets to 374 degrees, it becomes with 218 atmospheres. You get a supercritical fluid. You have what's called density merge. The liquid expands and becomes less dense. The steam becomes compressed and heavier. And at some point, they become of equal density the surface tension vanishes and the density of the liquid and gas equalize. And what you have then is a new phase. And that new phase dissolves all sorts of things, but it does maintain the fluidity of gas for flow. So it's kind of a supercritical water reactors. The good news is there's no heat jump. It doesn't boil at any point in the reactor. And because it gets real hot, you get 45% efficiency rather than 1/3 efficiency. The bad news is the water is hungry. It dissolves protective oxide layers off of metal pipes. So it destroys its own system. So the next thing to look at is metal sodium, just ordinary sodium. It's a liquid at 100 degrees, has a high thermal conductivity, and it can have low pressure operations because it doesn't expand when it gets hot. At 833 degrees, you're still at practically atmospheric pressure. It's compatible with fast neutrons. It has a little radioactive, but a relatively short half-life. It doesn't moderate, it doesn't participate in that. And it's good for what we'll go over, fast breeder reactors. It has a very low viscosity, so it's good for flow. But when there's good news, there's bad news. It's phosphoric, which means that it burns as soon as it hits oxygen. It's like a match, whoo, like that. And it's opaque, so you can't have your fiber optics in the tubing to see what's going on, in the inside of your tubing. It does have some induced radioactivity with a 15.5-hour half-life, so you have to have pretty heavy shielding around the primary loop, which adds cost. Sodium oxide, if it's captured in the piping system, causes corrosion. And metal sodium has what's called the moving metal problem. It will extract iron from one point in the piping and deposit it downstream. You get concretions of buildup of iron downstream, so structured tubing. And it also pulls carbon out of the metal. And as you may know, as you go from pig iron to stainless steel, you get progressively lower amounts of carbon, become progressively more brittle. So it's very hard, but it becomes more brittle. And when you have thermal expansion, it's brittle. It doesn't work very well. It's not a good combination. So how about the salts? How about Flybe? Well, fluorine, lithium, and beryllium. So it's lithium fluoride and beryllium fluoride. It's neutron transparent. But beryllium is good because it acts as a neutron multiplier. If you get a neutrons, they're flying all around anyway. If it hits beryllium, native beryllium, it hits the nucleus, and beryllium then divides. It goes back to it loses 2 neutrons because beryllium 8. So it takes on the neutron, and then does beryllium 8 plus 2 neutrons. So it multiplies the effect when you want more neutrons in the reaction. It's stable. It's a melting point of 459, which is low for a salt. The disadvantages: beryllium is a difficult metal to work with because of beryllium toxicity. And the lithium produces tritium, which can be a problem. If your lithium's hit by a neutron, it gives off an alpha particle, gives off 4 helium and some tritium. The lithium, the fluoride in there has a hunger for chromium. It extracts out the chromium, you get chromium fluoride. Chromium is part of, especially stainless steel. And if you get any water contamination, you get hydrofluoric acid, which can etch almost anything. So it's going to become very destructive. So it has to have great purity. So the molten salts, the bad news: corrosion materials, high temperature. Salt chemistry control must be very pure. It has engineering complexity and limited commercial experience. So that's what a lot of people are working with, but there's plenty of stuff to be overcome. And the last part that people are looking, the efficiencies of SMR, because they have a high surface to volume ratio, they lose neutrons to the outer surface, and then you lose your energy and you lose your reaction. So people working on neutron reflectors like beryllium oxide, stainless steel to contain the neutrons within the device. So I want to show you slow thermal reactors, which we all know about, and versus fast. Slow reactors, U-235, U2 goes up briefly, U-236, and fission. Great. That's the standard reactor. Fast breeder reactors use cheap U-238. You bombard it with a neutron. Where do you get that neutron? You get it from plutonium, which came from the beta decay of uranium, and that's one source, or californium, which is a very short half-life and it has spontaneous fission, as does U-239. So you get beta decay from the plutonium, and that will that's where you get the neutrons. But you get fission fragments. I'm going to show you in more detail because it's kind of hard to understand. So a slow neutron reactor runs out of fuel as the uranium-235 is built up, and it causes, and it's because of all the neutrons are flying around. Although there is some plutonium produced, it's likely to break down because the neutrons hit it and breaks down into stable elements. Now, if we look at the breeder reactor, this is really interesting to me. You get U-238 in a neutron, and eventually, with some more neutrons, it gets to plutonium, and beta decay gets to plutonium-239. And it gets a lot of it. So plutonium-239 will have alpha decay, which is 2 protons and 2 neutrons. And that takes a long time, half-life like 24,000 years.
And this is zero.
Oh, yeah, right. Yeah. Or californium, which is formed, can hit the plutonium and cause rapid fission. And you get 3 neutrons in stable element pairs. Well, that sounds pretty good. Now you can also get something which is seems odd, but it gets a neutron, you get plutonium-240. Plutonium-240 is incredibly fissile. It breaks apart. And it's considered a contaminant if you happen to be building a nuclear bomb in your basement. So just so you know, there's going to save a lot of work. Plutonium is so fissile. The way the atomic bomb works is you give all your fissile material in subcritical amounts. You have an explosive charge that puts them all together, and then they're releasing enough neutrons to blast each other apart to smithereens. Well, plutonium-240 is so fissile, if it's in your bomb, as it starts to approach the center point, it starts breaking apart. It's fissile there. And so you get a low-grade burning before it gets to the central point. So it becomes a fizzle, and the bomb just fizzles out. So you don't want plutonium in your basement. You don't want any plutonium-240 when you're building your nuclear bomb. So the fast neutron reactor, you have a slow neutron at U-238, U-239. You have eventually with a little beta decay, you're going to get some plutonium. And that's going to give off an alpha particle. We're going to go fission. The fission produces stable atoms and 3 neutrons. So what's going to happen here? Well, 2 of the neutrons, they can, see if they can do. There we go. They can hit some U-235 that you have in there and cause a fission reactant, which could produce uranium higher, it could produce uranium higher isotopes of uranium or plutonium. But also, one of those neutrons, 3, here, can go back up and become a slow neutron, hit 238, and create more plutonium, which will heat up the reactor. It goes around and around and around. This is like a eternal energy machine. And it will do that, except that with all the radiation, the cladding of the U-238 breaks down. The thermal cycling of the whole unit breaks down the outer edge. And it's one other thing that happens. Oh, you get the breakdown products of plutonium, the subnuclei. They start absorbing neutrons. They contaminate the system. So a fast neutron reactor won't last forever. It'll last for years, but it won't last forever. So U-238 is present in large quantities. It's cheap in a fast reactor. And the plutonium-239 is reprocessed, and they're put into slow reactors to provide a neutron source. So it breaks down fairly readily. Could plutonium find its way into the wrong hands? I can't imagine who, but it is something people have thought of. Now, this was I put this in. Gemini gave me this diagram, and I didn't alter it at all because I thought it was so awful. What they show is a liquid sodium fast reactor. Here's your main reactor. This is all liquid sodium, both the bath here and in the piping system. And so this gets radioactive. This sodium would be a little radioactive. You have your primary heat exchanger. So you make some steam, and this liquid sodium is going to come back to warm up again. And the secondary primary heat exchanger is going to send hot sodium here to a steam generator that gets it away from the primary reactor. This one's filled with steam. The sodium, it's a set primary. There's a steam generator here. So the sodium will go back here to reheat, and the steam will go out here. And here's our turbines. You'll notice that Gemini cluttered this with words. It was just so cluttered. I just want to show you what they'll give you. You can ask it to simplify, as Jonas taught me, to simplify and tell you what you really want, what you really want. But this is what you get for the beginning, because it doesn't really have a sense of how you illustrate things. So I thought that was instructive.
Jerry, go back to that for a second, if you don't mind. Why do you need two, I'm going to call them heat exchangers? Why do you need?
They're trying to get away from this high level of radioactivity. They're just trying to distance themselves.
So the first one is just to contain the radioactivity,
yeah,
and the second one is just to capture the heat.
Right. And they're just trying to get it because it gets real radioactive. Remember, sodium becomes radioactive, so it's real hot. It's not hot, and it's short half-life, so it's not dangerous in that sense, but it's real hot, radioactive.
Okay. Thanks.
So now let's look at the slow versus fast reactors. They solve different problems. The reliable grid power turbine, thermal or slow reactor is excellent. Fast reactor, it's possible to use it, but it's very costly. They'll maintain a lot of engineering problems. Fuel efficiency is poor. Fuel efficiency is excellent because it keeps making plutonium, gives itself its own fuel. Has long-lived waste destruction is cesium, strontium, plutonium, and americium, and what is CM?
California?
Yeah, no, that's CA. Can't remember what CM is.
Cadmium?
I don't remember. Somebody Google it. And here are the fast reactors, cesium and strontium, are only in the first 300 years, they say. And then plutonium, uranium, and thorium become more of a problem, in case you're wondering what you do for the next few hundred years. Weapons proliferation, very low because it's hard to get the plutonium out. It's very high because you breed a lot of plutonium. Operational simplicity is high. Fast reactors are not simple to operate. And of course, thermal reactors are very mature, and these are still developing.
Good. Before we leave the slide, see on this curium.
Curium?
Yeah.
That's the one that has no stable isotopes. Okay, thank you. Now, so we have our military grade here, the microreactor. Put it on a truck and drive it to your base. SMRs and the large reactors. Now, Palo Verde, the large reactors, 3 units, they're all about 1,500 megawatts. And the one in Korea has 7 units, each one about 1,200, 1,300 megawatts. That's a big one.
Is there actually,
Is that?
about Palo Verde, California?
Yeah. Now, ERCOT, I don't know what this is, what this stuff is. ERCOT, Texas is way ahead of the game. Texas has the Electric Reliability Council of Texas. It's a single authority. It dispatches power plants, maintains the grid, and oversees the wholesale electric market.
In Texas.
Me in Texas, son. To avoid federal regulation, they are not connected to the eastern or western grid. So the federal government has no role in this. Well, sometimes things don't work out the way you might. And when Hurricane Uri came by, they had 14 million people without power, 20 degrees Fahrenheit, and they couldn't import electricity because they had no connections. Son. But at Texas A&M, which is sort of the bellwether here, they have the Advanced Nuclear Reactor Working Group, and they're trying to, they've attracted some of the project, KROS, Natura, Terrestrial, and HALO. And at Texas A&M campus itself, they have the Energy Proving Ground and the RELIS campus. I had to look this up. RELIS stands for, they're real Texan, respect, excellence, leadership, loyalty, integrity, and selfless service. I love that.
Sounds like a Soviet.
I love that. But they're starting with a 5 megawatt micro reactor, get the lay of the land, just to figure out how to build it. This is the real beginning. This is the real beginning. There's one got a permit in Wyoming. I don't know if you saw that, but all he got is a building permit. They're behind. So the goals in Texas. Five megawatt pilot, 30 micro reactors, mostly molten salt reactors, which means what they call, the term is behind the meter use in data centers. The meter is what you get from the electric company. This will be closer and just provide to the data center. But when they're not using it, they're going to feed back into the Texas grid, not into your grid, into the Texas grid. So they're not going to power your car, people, don't worry. And they're building a $53 million nuclear research facility in Lockhart, Texas. So when you start saying, well, what are we doing in Massachusetts? Almost nothing. Texas is way ahead.
Are you telling me this is a lot of bull?
Well, it seems that way. And I wanted to tell you about like a seeming paradox, which we alluded to. At the end of the life cycles, the slow neutron reactors, the thermal reactors, run out of fuel because they consume their U-235. But the fast neutron reactors can produce more energy at the end of the life cycle than they started with because they end up breeding plutonium. So it's not really a paradox at all. Some people call this the nuclear reactor paradox, but it's not a paradox. So what are we doing with all this plutonium? Well, the idea was to put it in Yucca Mountain. And I've seen Yucca Mountain. Has anybody else seen Yucca Mountain? It's in New Mexico. You can see it from the highway between the flat highway, not the tourist road up to what it's called, the Turquoise Highway, but the flat one that goes straight from Santa Fe down to Albuquerque. You see it off the highway. It's 75 miles of desert to nowhere. That's where it is. The Indians said it was a sacred burial ground. I wonder how the Indians got across 75 or 80 or maybe 100 miles, I don't know where they were, across desert to get to Yucca Mountain to bury people. It didn't seem realistic to me, but it was declared off limits and they're not using Yucca Mountain. There's no volcanic activity, has no aquifers. It's a very perfect place to put the nuclear waste. So it's sitting at the Nevada National Security Site, just sitting there waiting for the next 24,000 years. They haven't figured out what to do with it. So now, coming to the end here, the SMR concept is, this is Claude, intellectually elegant, passive safety, no power, no pumps, no operator action, factory economics, horizontal efficiency, series production drives down cost, flexible siting, you can put the parts on transport. Then, as they said, this is the essence of it. The physics is sound, the engineering is proven in principle. Between design philosophy and a competitive deployable fleet lies a thicket of challenges. And this I got from, this is interesting, I got this from the combination of Adobe and ChatGPT. Adobe, their main product is Adobe Illustrator. The days of people like me making graphics on my graphics pad, for a book, those are quickly coming to an end. People are just going to ask Claude or Gemini is trying to catch up to provide the graphic. Adobe Illustrator, its market share is dropping like crazy. So they've joined, trying to bring some of their skill sets, I'm not sure what they are, to ChatGPT to use them as part of their AI. But the markets have decided that that's not going to work very long. The Adobe stock is going down, 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 down. So that it's probably the best of a bad deal they can make because they're caught in a technological discontinuity, basically. The graphics tablet, like my Ion graphic tablet, drawing graphic over and over until you get the things right. Those days are just going away. And by the way, now let's look at the actinides again. Actinium, thorium, here's your uranium, neptunium, here's your plutonium, here's your californium. One of the things you get from a U-235 when you hit it with two neutrons, you put all sorts of isotopes. You get 237 with some beta decay, you get Neptunium-237, Neptunium-238 plus a neutron gives you 238, with some beta decay, and you get plutonium-238. Plutonium-238 has a half-life of 87.5 years. And guess what? They put it on the Voyager. They have a unit 16 by 18 inches. They have using natural decay for heat. So that device, I'm going to use, it's been out there. It's been out there a while now.
It's gone beyond the end of our known solar
Yeah,
system.
yeah.
Wasn't that a
It's over the
seventies?
cliff, if you will.
What's that?
Wasn't that a
Over the
seventies?
cliff.
Over the cliff, yeah, right.
Wasn't that a seventies launch?
70s?
Something like that.
Yeah.
It's 50 years out, and but it's only half-life. It's still going to have heat.
It's still powering.
Yeah, it's still powering. It's only half-life. It's not the end life. It's
It
half-life.
takes like years or something for the radio signals to get back.
Oh, yeah.
Yes.
Yeah.
I think so. Yeah.
And so that's a pretty clever use of beta decay. So people think about this all sorts of ways. It's just so interesting how it's come up with.
Do they use the plasma as a thruster also? Do they use the plutonium to create plasma thruster?
No.
Not in that one.
No,
Not
that's
that
just
one?
no. That's just going.
That
That was just going. That was just going. It has escape velocity, as it were, with the solar system. It's just going to go. It's going to go. And again, with the Kent graph. This is from the Boston Globe. The tide's turning. New England's surprising embrace of nuclear power. The Globe has been anti-nuke forever. Now they're changing their tune. Now, you've all heard this, but it's worth saying. They say that because of the data centers, we're going to have to increase the amount of power we're producing in the United States by 50% by 2030. See any power plants being produced? That's impossible. They haven't even started. These are all theoretical. The SMRs are theoretical. But that's what the power demands are going to be. And it's frankly not realistic to burn coal.
And that's why the high school is $700 million.
Right.
They're putting a nuclear reactor
Right, they should.
below the
They're
basement.
putting solar, actually, spending the same amount though. Won't stop from spending. So trying to balance the issue of carbon dioxide in the atmosphere and our insatiable need for power. Personally, if you ask my opinion, and nobody did, I think we should admit defeat and say every major advance since the control of fire, the control of electricity, the control of nuclear, every major advance has been on the foundation of more power and cheaper power. And it just isn't feasible to increase CO2 generation to that degree. It just isn't realistic. It's just we'll be glowing hot, the whole planet will be hot. So we have to embrace nuclear power. You're gonna have to pay for it, you're gonna have to do it right. But just admit defeat. The great advances come with more power. And that's the way it is.
We'll find a way to convert
But they didn't
CO2
ask
to power.
They did right. They didn't ask me, but that's what I think. And it's just going to take that commitment to creating more power. We'll see advances that we never dreamed of. I've said in some other forums of that. When Steve Jobs invented the iPhone, he never dreamed that he would change the value of a taxi medallion in New York City from $750,000 to $15,000. He never dreamed that. Things happen when you have new inventions that you can't possibly think of. It's just the way it is. And when we have more power and more data centers and more everything, things will happen that nobody ever dreamed of. That's what's going to happen. So admit defeat, just do it. And that is the end.
Good job. Thank you very much. Really good.